One of the characteristics of this meeting is that most of the speakers really require no introduction. That's particularly true with our next speaker, Stephen Weinberg, since, after all, the whole timing of the meeting is to commemorate the 50th anniversary of his paper, A Model of Leptons, which Professor King nicely showed as his first slide introducing this session. Beyond his work on so many aspects of everything that we've talked about today, Professor Weinberg has also done, I think, an enormous service to the community by writing a series of extraordinary graduate-level textbooks. I personally learned cosmology from his book on gravitation and cosmology, and actually took his course on supersymmetry in Harvard in 1981 that provided the basis for a much later textbook on the subject. Beyond that, he's played an important role for both our field and for our civilization in his books for the popular reader, including The First 3 Minutes, Dreams of a Final Theory, and most recently his History of the Scientific Mind to Explain the World. He's really playing an important role as a public intellectual through his contributions to publications like the New York Review of Books. And rather than go on about the various awards that he's won, I'll just turn it over to Professor Weinberg.
All of the theoretical work that we've heard about at this meeting, all of the theoretical work that I've done and that most of us have done in our lifetimes have been within the context of the great theory of quantum mechanics that was essentially put in its modern form in the 1920s, starting with Schrödinger and Heisenberg, and then the unification of those two approaches in Dirac's transformation theory. I've been aware, of course, as we all are, of the reservations about quantum mechanics by some of the founders of the field, great physicists, de Broglie, Einstein, Schrödinger. And I thought, and I still think, that it was a tragic mistake for them, on the basis of their philosophical objections, to turn their backs on quantum mechanics and not participate in the exciting work on atomic and then nuclear and then elementary particle physics that followed in subsequent decades. Not only that, I thought that their objections to quantum mechanics were overblown. I thought there's nothing wrong with quantum mechanics. It has a perfectly good physical interpretation. Then, a few years ago, I started to teach a graduate course at Texas on quantum mechanics, which eventually turned into a book. And I found that I was unable to explain the foundations of quantum mechanics in a way that I found entirely satisfactory. It wasn't the old problems with waves and particles or the existence of probabilities or even entanglement, which bothered Einstein so much. I could live with all that. So I'd like to start by explaining what I find problematical, I wouldn't say it more strongly than that, about quantum mechanics, and then the effort to perhaps go beyond quantum mechanics and perform experiments that can detect departures from quantum mechanics. I have to remember what I was told about how to use this. There are three, my talk will be divided into three parts, two brief parts, which will describe what I take as the two approaches to the foundations of quantum mechanics that you find today, that I'll call an instrumentalist approach. Basically, quantum mechanics is an instrument for making predictions about what happens when you do experiments, and you shouldn't worry about it, what's happening out there. The realist approach that says, no, quantum mechanics really describes everything that's going on in the world, and it's all the time-dependent Schrödinger equation evolving along and describing what happens, including when you make a measurement. And I'll explain why I don't think these are satisfactory. Oh, by the way, whether or not I think they're not satisfactory, isn't it a little disturbing that the very theorists who are most satisfied with quantum mechanics don't agree with each other about what it means? You know, then you begin to suspect something. And the third, I will talk a little bit about the possibility that quantum mechanics itself, although a fabulously good approximation on the microscopic scale, may not be quite exact. The instrumentalist approach, which I would say characterizes, well, goes back to Bohr, Eugene Wigner, and has been expressed most eloquently these days by David Mermin. Quantum mechanics doesn't tell us what's going on out there. It simply provides an instrument for calculating, I said this before, probabilities of what happens when you make measurements. In particular, one of the fundamental laws of quantum mechanics is what we call the Born rule, that says if a system is in a state characterized by a vector in Hilbert space psi, and you make a measurement to see whether it's in any one of a set of states psi alpha that are mutually incompatible, like different eigenstates of some observable, then the probability that it's in the state psi alpha is the absolute value square of the scalar product of psi alpha with psi, and then normalized by dividing by the norm of psi alpha and the norm of psi. That's the Born rule. There are the problems that I find with the instrumentalist approach is, first of all, we really want to know what's going on out there. We don't want to know just what happens when we make observations. That, you might say, is sort of childish. It's just hoping for the moon. But I would say there's a more serious problem. Ever since Newton, perhaps I should say ever since Democritus, we've hoped for impersonal laws of nature that describe, that govern the world and that don't depend on the peculiar circumstance that there are intelligent beings that are out there making experiments. Even though, of course, when you make an experiment, in order to find out what happens, you have to know what the experiment was. The laws that govern that should not refer to people making experiments and choosing what to measure. And that is not true in the instrumentalist approach. And people like Mermin tell me they just don't worry about that. It bothers me if it doesn't bother everyone. The second approach that I mentioned is the realist approach. Now, I'm using realist not in the modern sense, meaning hard-headed and without illusions, but in a more medieval sense. The medieval realist was someone who believed in the reality of Plato's forms. And I mean realist in the sense of someone who believes that the wave function or the state vector is an aspect of reality. It's something that's really out there, the way we used to think that rocks and stones were out there. Reality is described by a wave function or a state vector that evolves linearly according to the time-dependent Schrödinger equation. It was pointed out in the Princeton PhD thesis in 1957 by Hugh Everett that this approach leads to a vast number of histories, a vast multiplicity of histories of the world. For example, if you have a state which is a coherent superposition of spin up and spin down, and you measure whether the spin is up or down, what you're doing is entangling yourself and your measuring apparatus with the spin in such a way that the pointer either points to up or down with probabilities given by the Born rule. But in fact, according to the realist approach, all that happens has to be described by the time-dependent Schrödinger equation, so there can't be any loss of coherence of the two. What happens is you go on having a superposition, but now it's a superposition of one state in which the spin is up and the observer says it's up, and the other state in which, and in fact everyone who reads his article says yes, it's up, and the other state in which the spin is down and the observer says it's down. The history of the world has essentially split into two histories. What is wrong with this approach, it seems to me, is first of all, I find this idea of it isn't just when you measure a spin, it just happens all the time. And you have an endless, countless multiplicity of histories. Actually, that provides a possible basis for anthropic calculations, but even so, it's unbelievable how many histories there are. Well, that's an aesthetic judgment. I can't find any logical deficiency there. But there's to me, a more serious deficiency. If all that's happening is the evolution of the state vector as governed by the time-dependent Schrödinger equation, then where does the Born rule come from? The Born rule that you use for calculating probabilities, because you can still do experiments repeating an experiment many times with the same initial wave function and finding that the probabilities of getting spin up and down are given by the Born rule. Where does that come from? How do you derive that from the Schrödinger equation? And it's not just a question of an intellectual challenge. If all that's happening is the evolution of the state vector according to the Schrödinger equation, then you must be able to derive the Born rule. And so far, no one has succeeded, although I have to admit some people have been very clever and come close. So we can argue endlessly about whether these are serious objections, but at least it seems to me worth considering the possibility that there is a further theory beyond quantum mechanics that's very close to quantum mechanics. But, for example, a theory in which the superposition between different states, like an electron spin being up and the observer thinking it's up, or the electron spin being down and the observer thinking it's down, that superposition naturally decays to one or the other, not just as a statement of what you mean by a measurement, but as an actual physical process. Well, you think it's hard to go beyond the standard model. Going beyond quantum mechanics is very much harder because there is not the slightest grain of experimental evidence that anything is needed. We have no help from experiment. Every experiment fits with quantum mechanics perfectly well. That's partly due to the fact that it's really, as a practical matter, impossible to create superpositions of different macroscopic states, like a state in which a cat is alive and a cat is dead, for example. So I think what we have to do is look in the microscopic level for tiny departures from quantum mechanics. And there is, in fact, already a growing literature on this. there are papers, I think the classic paper in this area is by Gherardi, Ramini, and Weber, 1986. Gherardi just died a couple of days ago, sadly. And then others, Philip Pearl, Milburn, Percival, and so on, continuing to the present. As I said, you get no guidance from experiment in this business, but happily you do get guidance from physical principles. It is extremely difficult to make a theory that goes beyond quantum mechanics that doesn't produce nonsense. And in a way, this is like the fact that it's very difficult to make a theory of electrodynamics that goes beyond the ordinary theory of electrodynamics that doesn't produce nonsense in the form of unrenormalizable infinities. In quantum mechanics, you can show that for reasons that, I think I went too far. For reasons that if you demand that in entangled states, it is not possible to send instantaneous messages, then you get a very strong constraint. You know that in an entangled state, where an electron with spin up has gone, where you start with spin 0, which is a superposition of one electron being up and the other down, or vice versa, and then it goes to a great distance, you still have entanglement. And if you make a measurement of the one spin, it actually changes the wave function of the other, even though they're very far apart. Can this be used to send a message? It is known to be true experimentally, but it can be shown that you can't send a message in ordinary quantum mechanics, because although you can change the wave function instantaneously at a distant site, you can't change the density matrix. And the density matrix is a quantum mechanical operator, rho, which has the property that if you want the average value of anything, then it's the trace of rho times that operator. And since this also gives you the average value of a square and a cube and so on, it gives you the whole probability distribution for the possible values of any observable you might get. You can prove in ordinary quantum mechanics that you cannot use entanglement to change rho at a distance, although you can change the wave function at a distance. That may surprise you, because you may think that rho is just a clever way of saying something about the wave function. That's not really true. If you know that a physical system is in any one of a number of states n, not a superposition, but it actually is in one of these states n, with probabilities p sub n, then rho is defined, it's given by sum over n pn times the projection operator on the state n, but you can't go backward. So that the density matrix contains less information than the statement I just made. Another way of saying that, there are various ensembles of states, each with its own probability, that will give the same density matrix. And therefore, and the density matrix knowing the density matrix does not allow you to detect the change in the state vector that can be produced in an entangled system by a measurement in one part of the system. So you need a formulation of quantum mechanics in which only the density matrix, in which the evolution of the density matrix only depends on the density matrix. If it depended on the state vector itself, then by using entanglement, you could send a message that changes the state vector, and that would then change the evolution of the density matrix, and you could detect that. And you don't want that. Now, the density matrix has to change linearly. The density matrix at one time has to be linear, a linear function of the components of the density matrix at another time. That just follows from, Tom Banks calls this Bayes' rule. It just follows from the way we think about probabilities. I can't imagine thinking about probabilities in which that wouldn't be true. And if you ask what is the most general linear, well, of course, then the density matrix at t plus dt is given by the density matrix at t plus some coefficient, which is the derivative, well, plus something called d rho dt times dt. Lindblad, most famously, but also at the same time, Guarini, Kosakowski, and Sudarshan, but all in 1976, wrote down the most general equation that the density matrix can satisfy, a first-order differential equation which preserves the key properties of the density matrix. First of all, that it's Hermitian, probabilities are always real, it's a positive matrix, probabilities are always positive, and the trace is always 1 because the sum of the probabilities is always 100%. And this is the most general such equation. It's called the Lindblad equation. And the work that I mentioned earlier by these authors is all in the context of specific versions of the Lindblad equation. And we don't have any fundamental understanding of what the Lindblad equation ought to be, but it's a generalization of the Schrödinger equation. You see, if you just had the first term, the minus I commutator of H with rho, H is just some Hermitian matrix, then that would be the time-dependent Schrödinger equation. That would be what the time-dependent Schrödinger equation gives you with a Hamiltonian H. And the other terms are corrections to that, and any experimental test should look and see whether or not these corrections might be there and how big they might be. Now, I'm not going to consider, I haven't considered, in fact, the most general Lindblad equation. Things become much simpler if you make a plausible assumption, which is that the entropy, which is minus the trace of rho log rho, never decreases. And that, as shown by Bonatti and Narnhofer, means that L doesn't necessarily commute with its adjoint, but the sum over alpha of the commutator of L with its adjoint vanishes. I won't show that. Now, then the question is how to look for tiny values of L. And I thought of atomic clocks, because atomic clocks are famous for giving you incredible precision. And precisions that particle physicists really never dream of. First, I tried to learn something about atomic clocks. First thing I learned about atomic clocks is they're not clocks. They don't tell the time. They are metronomes. They are frequency standards. An atomic clock sets a, well, if it's an atomic clock, the frequency standard is the energy difference between two states of the atom, typically the ground state called G and an excited state called E, divided by Planck's constant. And that provides an absolute frequency standard, and the purpose of the atomic clock is to expose these atoms to an electromagnetic wave, microwave or visible, and tune the frequency of the wave until it matches the frequency of this transition. This is done using a trick invented by Norman Ramsey in 1949. You first drive atoms into a coherent superposition of these two states. You do it by exposing them, I keep making this mistake, for a brief period, tau, to an external perturbation, which that is an interaction between the wave whose frequency you're trying to tune and the atom. You do it by sending the atoms through the wave. They're in a waveguide, and you let them go through an arm of the waveguide. And so that's the perturbation. That's the thing you add to the Hamiltonian. Now, I'm using ordinary quantum mechanics to analyze this part of it because this is not the part where the extreme precision comes in, where you could detect departures from quantum mechanics. Then, and this is the Ramsey trick, atoms are removed from the wave for a long time, much longer than this time tau, in which you drive them into this coherent superposition. The wave continues on going at its frequency, and the atoms go on oscillating with their frequency, but they're out of contact with each other. Now, just like two metronomes that are separated and go ahead ticking for a long time, when you come back and you compare them with each other, if they're still in the same phase, that is, the ticks occur at the same moment, then you know the frequencies are equal within an order of 1 over capital T, where T is the long time in which you separated. That's the trick. The accuracy is of the order of 1 over capital T. And then you expose the atoms again to the wave for a time tau to test whether they're in the same phase, and you measure the frequency at which you measure the fraction of atoms that are in the excited state, which you can do by observing the excited state decay into the lower state. And in ordinary quantum mechanics, the formula that you find is this one, the top formula. The probability that at the end of the process, starting with the atoms in the ground state, you find them in the excited state, is the sine square thing, where tau is the initial and the final, the lengths of the initial and final periods in which you're setting the coherent superposition of the atom. W is the energy difference divided by h bar, and no, I'm sorry. W is this thing here. It's essentially the strength of the perturbation produced in the atom by the wave when the atom is exposed to the wave. This W is actually the frequency of something called the Rabi oscillation, which is the oscillation back and forth between G and E if you expose the atom for a long time to external radiation at the frequency corresponding to that energy difference. And of course, it depends on the strength of the coupling between the atom and the radiation. So you have sine square of 2 tau W, which is not a very important factor, nor is it precisely known. It just sets the normalization. And then you have something that depends on how well you've tuned the wave to your atomic clock, cosine delta omega T, where delta omega is your error. It's the difference between the frequency of the radiation and the standard frequency, the frequency standard provided by the atom, the energy difference divided by Planck's constant. And clearly what you want to do is to find how far you are away from the maximum where the argument of the cosine is 0 and you just have 1 plus 1, which is 2. The excitation of the excited state is maximized if the wave and the atom have remained in phase during this long time t, and that requires that omega be equal to the frequency standard within a width, as you see here, of the order of 1 over t. Now, in these this is all pure quantum mechanics. In the generalization of quantum mechanics, you can assume instead that the states of the atom are governed by a Lindblad equation. If you assume that these states are stable states, then they have to be eigenstates of the operators in the Lindblad equation. And I'm making this assumption about entropy not decreasing. And then you find this result, which is very similar to the quantum mechanical result for the probability of exciting the atoms, except that there's this additional factor, e to the minus gamma t, where the new thing is this gamma, which is just related to squares of the coefficients in the Lindblad equation. If you don't see any corrections to the usual formula, I've asked, by the way, the atomic physics experts, suppose you put in a factor here like a quarter or a half, would you know that? And they say, oh yeah, that would stick out right away. So if you see the ordinary quantum mechanical result where there's a 1 here, then you know that e to the minus gamma t is pretty close to 1, and therefore gamma can't be of the order of t. It's got to be considerably less than 1 over t. And that's the way you look for these small departures from quantum mechanics. Now, of course, this has already been done by people who weren't thinking about departures from quantum mechanics, but just were trying to make good atomic clocks. And in the visible, you use aluminum-37 ions. They get a fractional accuracy in 2011 of 3 times 10 to the minus 7. That is, the width, this width of the resonance compared to the energy is 3 times 10 to the minus 7. And that shows that this quantity gamma on the previous slide is relative to the energy difference in the atom is less than a few times 10 to the minus 17. A very high level of precision. On the other hand, in the visible, this energy difference is pretty big. It's in the neighborhood of volts. You can get down to much smaller values in terms of energy if you go to microwave radiation. For microwave radiation, the best thing to use, I understand, I wouldn't know myself, is trapped 131 ytterbium ions. There, the Ramsey time could be as long as 600 seconds, achieved in 1995. And in that case, gamma is found to be less than 10 to the minus 18 volts. So that's a pretty small energy. Is it small enough? I don't know. I don't have, and neither really does anyone else have, a detailed, believable, specific model for departures from quantum mechanics. So I have no idea whether this is a significant limit or not. The question really is, what kind of departures from quantum mechanics distinguish macroscopic systems like physicists or cats from microscopic systems? Various people have made suggestions. One suggestion is it's gravity. Roger Penrose has repeated this in a recent book. Obviously, macroscopic systems have larger gravitational energies than microscopic systems. Another thing that I have thought about is that macroscopic systems have very close energy levels. For example, if you take a pointer that's free to swivel in a plane, and imagine its length is 1 centimeter, its mass is 1 gram, just to make the calculation easy, then, and think of the rotational levels of the pointer swiveling around. The low rotational levels are separated by something like 10 to the minus 24 volts. It's h bar square over the moment of inertia. And that's much bigger than this 10 to the minus 18 volts. So I don't know whether any of this testing of quantum mechanics at the microscopic level really tests anything that's relevant to the decay of superpositions in the macroscopic world. And one can just try. Clearly, in this business, what is needed is a bright theoretical idea that gives some guidance beyond just trying anything consistent with general principles. And that is also true in trying to go beyond the standard model. Thank you.
This is lovely. For anybody who's tried to teach quantum mechanics enjoys this very much. Have you tried to apply this to... Have you tried to...
You want to repeat that about it being lovely?
Anyway, have you tried to apply this to neutrino oscillations and see if we have any chance of, seeing anything happen there?
I can't imagine. Well, there is an analogy, I guess, to the Ramsey capital T. That is that neutrinos can travel very long distances, but we have no way of setting the initial superposition. I suppose, no, I can't think of any analog. There's no way of tuning the neutrinos, tuning one neutrino to match another neutrino. I haven't thought about it, though. Maybe you can.
You were saying there that gravity could be a factor that make the difference. So is anyone or you yourself try to incorporate the graviton and see if that close the gap on the...
Well, the only person I know who thinks that gravity has anything to do with this is Penrose, and I'm not a student of his writing, so I don't know the answer. I suspect he doesn't like to talk about gravitons, but I don't know.
You mentioned in the second part of your talk that the difficulty in making large-scale macroscopic coherent systems, so coherent CATs, is a big problem. Isn't that in itself a big problem for the second interpretation? I mean, why would we not expect to see macroscopic coherent systems?
I'm sorry, I didn't hear the question.
Doesn't the fact that we can't make large-scale macroscopic coherent systems, isn't that already a huge problem for the second of the interpretations that you talked about?
No, well, no, I don't think so. I think in the second interpretation, even though you're talking about, in the real world, you're always talking about systems whose precise quantum state you don't know, still the calculations have to be done, according to their point of view, by actually imagining an ensemble of such states and considering the evolution of the state vector for each one of those states. And you have to ask, and you make assumptions about the probability of getting certain values when you make measurements at the end of the time process. You get in. It doesn't correspond to what actually you do, because you never really know what the probabilities of individual quantum states are. But it's the way they think about it, and the way they think about it leads to reliance on the Born rule, and the Born rule just comes out of the blue without being derived from the time-dependent Schrödinger equation, which is supposed to account for everything. It has to be taken as an independent principle, and then you're back in the problems of the instrumentalist point of view, namely, how can the laws of nature refer to people making measurements? Suppose people never appeared. There would be no nature, or even if no physicists ever appeared. One can imagine all kinds of utopias. There's another question. Gerard?
Yeah, I'll just make a remark, if I may, and a question.
That doesn't seem to be working.
The remark is you could do the opposite exercise. You just take a completely classical system, like a planet moving in an ellipse or whatever, and discretize it. You can use quantum mechanics as a language to describe it. You change nothing in the planet, you change nothing in quantum mechanics. So the Born rule and many of the questions that people always ask come out completely naturally, and quantum mechanics just comes out. The only thing is you don't know the initial state. And when you look at atoms or molecules or something, when you do an experiment, or elementary particles, you never know with what state you began. So your only guess is you take something, and that's where that is the superpositions also come in. When you extend this picture further, you find that many questions people ask all the time about quantum mechanics, about entangled states, about the Born rule, and about the measurement, comes out completely naturally. The one difficulty, however, is that we want something that generates anything like the standard model this way, and that's a very hard question to ask.
Well, I haven't looked at it in that way and can't really comment on what you say, but it suggests that I should clarify that my problem is not with the Born rule itself, but with its status. If it is a fundamental principle, then it's a principle that refers to people, which seems improper. Now, I'm gathering from what you say that it's not a fundamental principle, that it's something that just comes out of this sort of calculation. But I don't see how that can be without an independent probabilistic axiom in there somewhere. If you have, it's a bigger problem in a way. If you have a completely deterministic theory, where do probabilities come from? Well, you would say, I suppose, that they come from your lack of knowledge of the initial state.
Exactly.
Yeah.
That's very surprising, because many people say in quantum mechanics probabilities are completely different from what they are in a classical system. In a classical system, you don't know the exact outcome because you don't know the initial state exactly. Now, my claim is it's exactly the same. The reason why you can reduce all the probability interpretations of quantum mechanics to our ignorance concerning the initial state.
And what happens to each one of the states that you have initially? Is it just the time-dependent Schrödinger equation?
Yes, and then if you would know the initial state, you would have your initial wave function as a delta peak, and in a very special basis. So the difficult part of the argument is that I have to attach a basis to the entire set of states that the system can be in, and a classical system evolves from a certain state to a certain state.
But don't you
delta peaks?
I'm sorry.
Delta peaks continue to evolve into delta peaks.
But don't you somewhere say that if at the end you want the probability that the planet is in one location rather than another, you have to do an integral over the space using an absolute value square of the wave function, and that is the Born rule. In other words, don't you at the end have to do a calculation that depends on assuming the Born rule?
No. Well, you do put it in, but there's nothing else you can put in than that.
Oh, well,
that's,
look, I'm saying that there's nothing else you can put in.
But I'm saying you get a completely consistent picture this way. The only thing is that in the real world, we don't know what those realistic states are.
No, but I think still, I've had this argument, I think, it's the same argument I think I've had with Tom Banks, that you're still putting in an assumption that the absolute value squares of components of the wave function weight the different probabilities you will get. And I think that's just assuming the Born rule all over again. I don't think you're escaping the assumption.
No, but
Maybe we better.
I think we have
better
a private
argue about
discussion
it.
because I can explain exactly what I mean with this.
Okay. All right. Thank you.
Thank you.